When you point your phone camera at a sign in another language, it instantly swaps foreign words for a perfect translation on your screen. But underneath that speed is a massive obstacle. Computers don't look at a scene and see streets, buildings, or people the way we do. They only see a chaotic, endless grid of raw numbers that represent the colors of individual pixels. To find something specific in that ocean of numbers, the computer has to use a methodical strategy. Imagine you are trying to find a specific face on a giant poster, but you are only allowed to look through a tiny rectangular hole cut into a piece of cardboard. You would have to drag that cardboard cutout across the entire poster, inch by inch, checking exactly what is inside the hole at any given moment. In computer vision, this foundational concept is called a sliding window. By breaking an overwhelmingly complex, multi-million pixel image down into a sequence of tiny, sequential yes or no questions, the computer sorts through the chaos. Before a computer can scan an image for a target, say a pedestrian walking down the street, it has to be meticulously trained on exactly what that target looks like when it's squeezed inside that tiny, fixed rectangular boundary. On the left side of this diagram, developers train the system with thousands of positive examples, perfectly cropped patches cleanly framing a person. On the right, it sees images of trees and walls to learn what is not a person, knowing exactly what to ignore. This simple game of yes or no training takes a completely empty digital box and turns it into a highly specialized detector, ready to instantly judge whatever falls inside its frame. In this photograph, the scanning begins. The computer places a fixed-size digital window in the top left corner to check for a match. Finding nothing, it shifts slightly to the right, continuing row by row in a rigid trail until the entire image is mapped. As the window moves, it takes a specific stride or step size with every shift, much like a person walking, to make sure it covers every inch of the photograph without missing a spot. This introduces a serious logic problem. What happens if a person is standing very close to the camera, making them physically too large to fit inside the computer's tiny fixed window? The solution is to shrink the actual photograph itself, running the exact same tiny window over the new, smaller image. As the world gets smaller, the window captures a wider view. Because the computer manipulates the scale of the outside world rather than the size of its own tool, it maintains its accuracy regardless of how far away the target is. This side-by-side comparison shows us why detecting text on a sign is different than finding a pedestrian. Pedestrians all share a very similar tall and thin shape, but words can be any length, from a single letter to a long sentence. Because of these unpredictable lengths, the sliding window only looks for small pieces of letters. In the bottom left image here, we see a scattered map of bright white spots where the computer sees text fragments. To solve this, the computer uses a technique that forces those scattered points to grow. By expanding these tiny specks of white, the computer makes them bleed together until they form solid, continuous blocks. Finally, the computer evaluates these merged blocks. It draws red rectangular boundaries around the wide shapes that look like real words, and it discards the tall, unusual shapes marked here with red X's. This expansion technique gives a rigid, square window system the flexibility to capture objects of totally unpredictable shapes and sizes out in the real world. At this point, the computer has successfully locked a single box around a whole word. But to actually read it, it must isolate every single letter inside that box. We do that using a one-dimensional sliding window. This is a tall, incredibly thin sliver of a window that is restricted to sliding horizontally from left to right across the word. The brilliance of this thin window is that it isn't looking for letters at all. It is trained entirely to find the empty space between the characters. When it finds a gap, it drops a blue line, acting like a knife to separate the A, the N, and the T. By specifically searching for the absence of data, the system cleanly slices a complex block of text into individual characters that are easy to analyze. This summary chart brings the entire process together. In row 1, the system uses the slide-on window to scan the image and lock onto a text region. Moving down to row 2, the system uses the narrow, one-dimensional window to chop that region down into isolated individual pieces. Finally, in row 3, those isolated pieces are passed through a sorting step where the computer compares the shape of the A against its digital alphabet to confirm exactly what letter it is. Every time your phone translates a foreign sign or focuses on a friend's face, you are watching an invisible, relentless grid of tiny digital windows scanning our world at light speed.